Well, I guess we can get started, everyone. Welcome back, folks. We're on week 13 of the 16-week semester, but that means we really don't have a lot of course content left over. We are going to have a normal week on this week right here with the potential review on Thursday. But our exam 3 is already going to take up a big amount of time on the next week. So we'll have just 2 instructional days next week. Closed week, we're going to just finalize our last concepts. We're not going to introduce a new section. So this is going to be primarily just a review week. We're really there, and the major thing now is exam 3 is on the table. We'll have our third exam when we come back a week away from today, next Monday, and it's only specifically these sections through here. So it's targeted to sequences and series, where section 11.8 is really where we're dealing with power series the very first time, but we're really just using the ratio test often in that one particular section. So here's the formula sheet for exam 3. We've been looking at it all along. It's basically just this stuff with this information to support section 11.8 as well. So this is the trichotomy of what could happen when we go to use the ratio test on a power series like this one right here. So that's our exam 3. And with the same exact parallelism, version 1 is blanked out lecture notes. So they're like worksheets now. Those problems are just as good for practicing exams. Version 2 is the same. These are blanked out worksheets for the actual homework questions themselves. And this is just as good as our source for questions. Finally, version 3, this one is brand new exercises. It has solutions at the very end. This gets a little bit more challenging. You'll notice some of these are more concept questions. I'm not going to try to actually ask these more challenging questions on the real exam. So think of always version 3 is just if you want to go a little bit beyond on your studying. But version 1 is what we did in class. Version 2 is what you did in your homework. And I try to base my exams to be very close to both versions at the same time. So these would be really good sets to look at as well. When we come back on Thursday, I'll be happy to take any number of questions that we might have on any of this content. But any questions at the moment? Okay, and as far as the rest of the course goes, section 11.10 is the final one in all of chapter 11, so we're basically there. Congratulations, it is quite a bit of work to get through chapter 11, but once you get there, it's kind of cool to see how it completes. We're doing this in 2 parts, part 1 being the more mechanical part, and part 2 just looking into some applications of this kind of work. So currently we're in section 11.9, but 11.9, we're looking into this formula that came from the geometric series. This is a Maclaurin series. It's a Maclaurin series for 1 over 1 minus x. We're just adapting it in lots of different interesting scenarios in these problems as kind of a warm-up before we get to 11.10. So that's where we're at. We're going to finish off 11.9 and get started on that next section today. Any questions at all, folks, before we begin? Okay, let's take a look into this. We left off right here. Kind of a nasty page to take a look into, but let's look at this carefully. What we want to do in example 2 is, let's grab this just as an extra visual. Our goal in example 2 was to take a function, the one in green, natural log x squared plus 1, and represent it as a power series. So something like this on the right. We couldn't do it right away with how part A starts. It's natural log x squared plus 1. But if you differentiate that thing, we got 2x divided by 1 plus x squared. And we can make it fit that format with enough algebra. We got to it in this step 2 right here. Factor out 2x, include double negation. And this formula above just turns into this for that particular example. We expanded this out, got to the part in blue. So now here's f prime of x again. So f prime of x is represented this way, but if we integrate, we relate f of x to its derivative. So f of x was natural log x squared plus 1, the thing we wanted the power series representation, and we have one on the right, we just had to integrate. But this is a normal kind of integration. 2x to the power 2n plus 1 becomes 2n plus 2, divide by 2n plus 2, and that took us to this step here. We solved for the constant, that's the work below, but then we jump down to this statement. The Maclaurin series representation of natural log x squared plus 1 is all of this stuff. radius of convergence 1. Definitely a weird problem, but just to get some more practice on this, we'll try it out a second time. So here's our next problem down below. So with the information we looked into just barely, let's try this out again. On x squared, tangent inverse x cubed. This one feels worse, and I guess it definitely is, because this time we have a couple functions. We're trying to relate to 1 over 1 minus x. First factor x squared is messing all this up. We can't just differentiate the function and get what we want, because now a product rule is going to be mixed in with this. So here's a new strategy. What we do instead is just take one part. I have no chance of representing x squared as something in this format, but the derivative of tangent inverse does take us to 1 over 1 plus x squared, tangent inverse x. That's really close to this format. So we should define tangent inverse x cubed as g of x. Let's say it right here. Let g of x equal tangent inverse x cubed. So now that we have that g of x, we're going to come back to the f of x function, but x squared is just hanging for the moment. First, differentiate g of x. The derivative of g at x goes like this. So there's our structure through the chain rule. The derivative takes your x cubed, drops it down below right here. And then we just have to differentiate x cubed again. We get 3x squared in the numerator, 1 plus x power 6 in the denominator. And that's really close to the right format. We have the 1 in the right position. We'll use double negation as before and factor out 3x squared. So now it's at 3x squared times 1 over 1 minus negative x power 6. So we have the 1 above right here, as we need. We have the 1 below, the negative sign as well. So this whole part, negative x power 6, is that x part after the first negative sign, and it goes right in there to power n. So now it's equal to 3x squared times a sum from 0 to infinity of negative x power 6 raised to power n. So we used up this formula almost entirely, except in some sense, missing this could actually take a lot of work out of this. Because if we don't use that information there to get the radius of convergence, we might have to test, say, right here on this power series, maybe the ratio test on what the radius is. But whatever the radius is right here won't change even after we integrate, even after we multiply by x squared. So we should just find it right at this step. Let's say this works provided in absolute value, whatever x is. In this problem, it's negative x power 6. It just has to be less than 1. But then this would imply x power 6 itself is less than 1. You can take the 6th root of both sides of this new equation right here to get, upon the 6th root, it's just the absolute value of x, less than 1. That directly tells us the radius is 1, and that's going to stay the same value through the rest of the entire problem. So our work is completely done on this theorem right here. Let's move it out of the way. Now we have to get back to what g of x is. So relate the derivative to the original function, and then relate the original function back to f of x. Once we do all that, our work is 100% complete. So let's write in g of x is the antiderivative of the derivative g prime at x dx. Next step, we're just making a big substitution. So we're integrating this whole thing right here. Oh, you know what? Before we do that, we might want to do a little bit of extra work on this. absolute value of x less than 1, radius equals 1. Let's just recopy that so I can delete these. One thing that I forget about these problems that I think we did mention last time, you definitely want to simplify this as much as feasibly possible, because we don't want to integrate 3x squared times an infinite product. Our theorem isn't going to support us on that. Let's just rewrite this as 3x squared, sum from 0 to infinity, negative 1 power of n, x power 6n. So all I did here is just distribute n to the negative 1 that's multiplying and 6 power x to the power 6. Then we can leave 3 on the outside, but x squared can now factor inside or distribute inside and goes from 0 to infinity. This is negative 1 power of n. And this really is one major distributive law when you think about it, because this is just infinitely many different plus signs. X squared distributes in through that, combines with this power to x power 6n plus 2. Radius of convergence still 1 even after those steps. So now that's the g prime we actually want to integrate. Let's write it in just like that. 3 times an infinite sum from 0 to infinity, negative 1 power of n, x to the power 6n plus 2. And here's this really wild statement. The theorem that's above, right where we are on the notes, is kind of hard to look at. I mean, here it is. This is a big theorem. But the whole content of this theorem is really just to say the differential operator here can go inside an infinite sum, and so can the integration operator right here. You can distribute across infinitely many different terms and integrate on the inside. So we apply that theorem here and rewrite this integral problem and take the integral sign, drop it right there now. So this is 3 times, maybe before the 3, that should be fine. 3 times the sum from 0 to infinity, negative 1 power of n, integrate x to the power 6n plus 2 dx. So that's where the integral sign lands. On the next step, we're actually integrating. So g of x, which was equal to tangent inverse of x cubed, is equal to, when we perform this integration, we'll get a constant. I'm going to put out in front c plus a sum from, well, 3 times the sum from 0 to infinity of negative 1 power of n. Then we integrate. It looks really weird, but same exact ideas. Power goes up by 1. So this is x to the power of 6n plus 3. Then divide by the new power. 6n plus 3 is in the denominator. And this is just 3 multiplying. All of that result there. We need to solve for the coefficient c next. But to do that, we just pick the center value. Set x to 0. That's the center because it makes the term here where x is 0 itself when substituted. If x is 0, then that would imply on the left we have tangent inverse 0 equals, on the right it's a constant plus 3 times sum from 0 to infinity of just 0. Once we plugged in 0 in for x, we don't have anything here any longer. If you didn't write anything at all, that'd be appropriate as well. Then also tangent inverse of 0 is 0 because tangent of 0 is 0. So the constant is 0 as well. It's one of those weird problems where if we weren't super mindful of that constant, it may not have hurt us because it's 0, but it's not guaranteed to be 0 in every single problem that you could come up with. So this is a good check to do in the middle. So finally, what this tells us is g of x, which is tangent inverse x cubed, can now be rewritten as, let's focus on the function tangent inverse x cubed, equals 3 times a sum from 0 to infinity, negative 1 power of n, x to the power 6n plus 3, over 6n plus 3. We can write here just as a reminder, the radius is still 1, even after doing that integration. But now we have to move back a bit Go back to the original problem, which is this one. We wanted a power series representation of x squared tangent inverse x cubed. The original f of x, let me write it down from memory. Let's say here, therefore, f of x, which is x squared, tangent inverse x cubed, it now has a representation because we found out how to represent the hard part. Tangent inverse x cubed is just this up here. We'll multiply it by x squared. All it's going to do is up the power by 2. It'll be 6n plus 5 here. So finally, we can say, therefore, f of x is x squared times sum from 0 to infinity, negative 1 power of n, x to the power 6n plus 3, 6n plus 3 below. So that's the substitution step. Last step is x squared just increases this power. So 3 times the sum from 0 to infinity, negative 1 power of n, x to the power 6n plus 5 over 6n plus 5. We've got it, folks, this weird function, x squared. Oh, sorry, say again. Oh, no, it shouldn't have had. That was my miscopy on there. That should have still been 6n plus 3. Thanks for spotting that. 6n plus 3 from that copied over. And the radius itself, still the same as well. Radius is 1 on this. But other questions or comments, folks? Getting that power series nailed down? Okay, well, we've got it. The next section is called Taylor series and Maclaurin series. Let's duplicate that comment we made at the start of class. This is a Maclaurin series representation since the center is a equals 0 on this particular power series. If the center was anything else, maybe a equals 1, we would have had x minus 1 to the power 6n plus 5, but then we would have called it a Taylor series. That's the only difference between these fancy words, the Maclaurin and the Taylor series, whatever its center happens to be. So in section 11.9, we really are doing those kind of problems in 11.10. It's just kind of a warm-up section leading up to it. What we want to do next is just a couple applications on what all this stuff is good for. If you had a representation like this, you'd want to know, what do we use it on? What is it good for? How does it even help us out? So that's what the next problem is all about. But any last questions, folks, on finalizing this one? Okay, let's try it out again. On example 3. Here's where our methods start to really help us out in chapter 11. We can do an approximation on this integral if we really wanted to as a definite integral. Finding an antiderivative, though, is not going to be easy on something like this. Not saying impossible. You might be able to work, say, something along the lines of a trigonometric substitution on this, but it could take a lot of work to make that actually go through. You probably have to call trigonometric substitution multiple times, and the algebra could get really hairy on this. And for other examples, maybe not that one, but for other examples we'll see in section 11.10, something like this. Or how about rather sine x minus 1 over x. This is even worse than this problem over here. This one has no elementary antiderivative, but our methods, writing down a function like this, is effective for it. This one is just as bad, e to the x squared dx. So this is really what it's all about, trying to find nice antiderivatives so that when we need to go and really use the fundamental theorem of calculus, we don't have to use part 2 to come up with an antiderivative. Convergence on power series are often also really fast. So if we really want to integrate this from 0 to 3, first step is get the power series representation, then we can work with it. And the convergence is so fast, this could be less work for remarkable accuracy than doing something like Simpson's rule, trapezoid rule. So let's give this all a try. Evaluate the indefinite integrals of power series means we first want a power series. We need to take x over 1 minus x cubed, 1 minus x power h rather, feed it into the geometric series, and that just automatically gives us one. So here's how we're going to start. Take all this. Let's say x over 1 minus x power 8 already pretty much fits the format. We could factor out x if we want to really match it up. X times 1 minus x power 8 gives us x times the x power 8 in this spot goes right inside here. So sum from 0 to infinity, x power 8 to the power n, then this is going to be equal to sum from 0 to infinity, x to the power of 8n, almost there, sum from 0 to infinity, x to the power 8n plus 1. So in the last step, all I've done is distribute x inside, bumping up the power. Radius of convergence on this one, if you have to guess, anyone see what it ought to be? Just 1 again. Yeah, that's one of the things you might have noticed here. If I have a high power on x, but there's no coefficient in front of it, then x is just going to be less than 1 in absolute value. If we track that step really carefully, though, here's what it would look like. That's the x power 8 that gets plugged into this spot. So x power 8 would have gone right here, and we would require x power 8 in absolute value to be less than 1. But that's a really odd little statement there. If x power 8 is less than 1 in absolute value, that means it's less than 1 just like this. We could take repeated square roots or just an 8th root, but an even root on both sides brings back the absolute value. And the 8th root of 1 is just a 1, so we just keep on getting that foregone conclusion. Any power here would give us that same exact result, in other words. So now coming back down, we can now say that this whole thing could be represented this way. And now we just make the substitution. Let's say, therefore, it's a good time to say it because was like the main work right there. Antiderivative of x divided by 1 minus x power 8. Looks like I forgot my dx on that one. Sorry about that. It is a weird omission. One person on exam 2 noticed that there was a dx missing as well. Good eye to that person. I'll try to keep a closer look on the dx's. By substitution, we're replacing the thing in green with all of that. So now we're integrating a sum from 0 to infinity of x power 8n plus 1 dx. That means our job is basically completely done at this step. When we integrate, I always put the constant in first, only because if I put it after the sum, it could be misinterpreted as being part of the sum itself. This makes it more clear as something extra, not inside the sum. Then we sum again from 0 to infinity. We're just doing an antiderivative right here. You don't have to show the extra step with the integral sign pushed in unless you want to show it for clarity. But integrate all that, and you get x to the power 8n plus 2, division by 8n plus 2. And for free, we get the radius of convergence from the geometric series test. Radius is still 1. It doesn't change by doing any kind of integration or differentiation. We don't even have to solve for the constant. This is an ordinary antiderivative problem. It's not like the work of finding the exact representation of tangent inverse. We needed to solve that constant because there's only one tangent inverse. It's not whichever constant you choose right here. It had to be solved. But down here, it really is any constant you want. The indefinite integral gives you a family of antiderivatives, and this is one particular one. Choose any value of c, and you get another one. That one's a fast problem out of nowhere, but does that make sense to folks on what the process looks like? Okay, so this is, again, the major goal of Chapter 11. The major reason we want to do all this kind of stuff is this method is actually really quite powerful. And it sneaks into your work in mathematics, engineering, the sciences, chemistry in the oddest of ways. Here's our example of how this can really make it in. to an ordinary applied problem. Section 9.5, very last problems we looked into were applied problems. And this was a complicated looking differential equation because the context was complicated. But the differential equation itself wasn't so bad. And yet, we make the differential equation even simpler. This can come up in ordinary, routine, applied situations, just like in the circuits diagram. But that came up. The antiderivative of e to the x squared. No elementary antiderivative whatsoever on this thing. But if we could come up with the Maclaurin series for e to the x, then we can use these same exact tricks. Feed the Maclaurin series for e to the x, the e to the x squared function to get a new representation. Same idea as what we've been doing down here on these notes. That was then going to allow us to actually get a nice antiderivative right here, not something like this one. That's the fundamental theorem of calculus part 2. If you want to evaluate this function, you pick an x value, say 5, and now it's trapezoid rule or Simpson's rule or some other approximation method. However, if we had a power series, convergence is really fast because we're going to see factorials in the denominators for e to the x. That means only 4 or 5 terms is going to give you shockingly accurate values. So that's the motivation behind what all this stuff is doing, where all it's going. And that's why the last example is an integration kind of problem, just to remind us of that application down the line. There's one more to do just for the sake of practice, slightly harder than this one. But any questions before we give it a try? Okay, let's try out our part B on this then. Part B is x cubed natural log 1 plus x. We want to integrate that thing as well. But just like the last exercise, part B, the idea is we want a power series representation through the formula on the bottom of this page. But we're going to do it for just one factor, natural log 1 plus x. So let's start up that process. We'll get a representation for this, then we'll bring it together with the x cubed, then we'll just integrate whatever we've got. Let g of x, to start it off, be natural log 1 plus x. First thing we do is differentiate. G prime of x is 1 over 1 plus x, multiply by the derivative of 1 plus x through the chain rule, and now we're done. We get exactly that. That means it's automatically ready to fit. Here, we just need to force the negative sign. So write in 1 over 1 minus negative x. Now that identifies what the x value is. In the formula below, highlighted in yellow, our problem is going to use negative x in all those 3 positions down below. So now we go to this stage, write in sum from 0 to infinity, negative x power n. Next, also state the radius of convergence. We would be taking the absolute value of negative x, set it equal to less than 1. But then that just implies absolute value of x is less than 1. And so radius of convergence on this, exactly 1 as well. Usually nothing too fancy with the radius of convergence on these kind of problems. Now that we have all that in mind, let's see, what should we do? Let's simplify this a bit, because we have to integrate it on the next step. So let's rewrite this as now g of x equals natural log 1 plus x, which is then going to be equal to sum, or excuse me, the integral of g prime of x dx. And again, I'm forgetting, before I put g prime of x dx in there, let me take one more line right here. This is sum from 0 to infinity, negative 1 power of n, x power of n. So natural log 1 plus x. Here I'm just putting in the substitution of g prime of x is going to be equal to integrate from 0 to infinity, negative 1 power of n, x power of n. We're almost there. We can say on the left-hand side, natural log 1 plus x equals, we're about to integrate, so now we have a constant of integration, c plus a sum from 0 to infinity. Inside here, that's just now regarded as a constant, no change. The variable is x, and I think I did forget a dx on this. Let's throw that in there. My omission is in that highlighted box there. -1 power of n, antiderivative of x power of n, is x power 1 more, n plus 1, over n plus 1. So now we've got just about everything in line, but we still have to solve for the constant c in this process. The reason being is we're looking for the exact representation of natural log 1 plus x. There's only one constant c that'll do the job. Almost guaranteed to be 0 again, but we have to show it, so here's that step. Pick the center. It's a value set to 0 again. It's the value that makes x to a power go to a 0 to find the center. Then take the left-hand side at the center. It's going to be natural log 1 plus 0 equals a constant c plus right-hand side at the center is just one big 0. On the left-hand side, this is just natural log 1 equals the constant c, but natural log 1 is 0. And so that tells us 0 right here. Again, that's an expectation, so nothing too different from what we've seen in the notes. Natural log 1 plus x can now definitely be re-represented as a sum from 0 to infinity, -1 power of n, x power n plus 1, over n plus 1. And then come right up here, just grab your radius, set it to 1, because this avoids us doing a ratio test right in the middle. It's a foregone conclusion and radius really is 1. Well, next step. So we have to bring in the entire function, x cubed natural log 1 plus x. But this is where we're pretty much wrapping it up. Let's write in antiderivative x cubed natural log 1 plus x dx becomes integrate x cubed times this entire power series right here, but that's just going to bump the power up to n plus 4. Let me write in just to show the actual step on the notes. Sum from 0 to infinity, -1 power of n, x power n plus 1 over n plus 1 dx. So that's what we're integrating next. We combine this together and get a sum from 0 to infinity, -1 power of n, x to the power of n plus 4, divide by n plus 4, dx. Now we mentioned we're skipping the step where we show another line, integral going right over here. If you want to show that line, not a bad idea. Let's just indicate it this way. Oh, sorry, say again. Oh, same exact mistake. Thanks for spotting that one. Must be some kind of pattern on how I'm trying to copy these down. So that one should have been a 1 right over here. There we go, we've got that. And this integral sign is just going to settle affecting n plus 4. So here's our overall result on this one. This time when we integrate, we don't solve for the constant c, because this constant c is just a result of a general antiderivative. So it belongs there this time. We don't need to solve. Sum from 0 to infinity, -1 power of n. There's the big integration step. It's now x power n plus 5. But because we have a new power, we have to take the old power in the denominator, n plus 1, multiply it by the n plus 5, the new power that emerged, and our job is done. We just want to restate the radius because there's no further testing you would ever have to do on this one, only because we use the geometric series test. This is such an important comment. If you did use the ratio test right here, you would have to do 3 different tests really, because the ratio test fails at the boundary. But the geometric test does not. The geometric test guarantees convergence right at the boundary and at greater than 1. So this is far and away saving us like easily 15 minutes of time, just saying radius is 1 from the initial steps. We did it, folks. If we ever have to integrate x cubed natural log 1 plus x, Probably integration by parts is going to be effective, but this is another route, just a slightly harder problem. Any other questions at all, folks, running through these kind of methods? Okay, so section 11.9 won't make it onto exam 3, didn't make the cut from last week. That's also kind of a weird section, in all honesty. We might have one or a couple problems from this section, but mainly it's going to be this kind of step, integrating something or differentiating something. And the reason is, like we mentioned, 11.9 is really just the warm up to this section. We already were looking at Maclaurin series, and now we're going to go more general and also look into Taylor series as well on the bottom of these notes. So we're breaking up this section into two parts because it is a pretty big section, but really it's not as bad as you might think. It's all about just carefully tracking the definitions. And the very first definition we have to carefully track is this power series representation. We know exactly what that is. We're really looking into a Maclaurin series in the right sense. So let's assume F has a power series representation centered at A. Well, that means it could be a Taylor series if A is not zero. Let's say that here. If A is not zero, it is a Taylor series. Might as well finalize this entire statement. We've said it before, but let's say it again. We're in the section of this now. If A is zero, it is a Maclaurin series. The interesting historical background on these gentlemen, if you read it in the margin, is if this work is really due to Taylor, but Maclaurin used this work a lot, and so his name kind of got attached to it, but it was often when the center was zero. The name Maclaurin series just stuck, even though it was Taylor's work where a lot of this came from. But in any case, we're writing down a power series centered at A. Here's what it would look like. First, we'll do F in sigma notation. F of X is going to be a sum from 0 to infinity of Cn, these are the coefficients of the power series, times x minus a to the power n. The a value minus the sign is the center. So here it is in sigma notation, but what we really want to investigate what a Taylor and Maclaurin series look like is to expand it as well. So let's rewrite f of x as a function is also plug 0 inside here, and we'll get C naught, or C sub 0, x minus a to power 0 we regard as 0. Even if it's 0 power to 0, we use that as a convention. Excuse me, we regard it as 1 if the power here is 0. Anything to the power of 0 is 1. And by convention, we're regarding 0 power 0 as 1 as well. So we up the index to 1, and we'll get plus C1. X minus a to power 1, so just x minus a, up to 2, C2, x minus a squared, and that's the pattern so far. We actually need a good number of these terms, so let's write out maybe up to C5 plus C3, x minus a to power 3, C4 times x minus a power 4, C5 times x minus a to power 5, and it does go on forever. The sum is infinite, like we indicated. This will give us enough terms for the very next step. So example 1, again, really just a warm-up question. We're taking another look at what did we mean when we say power series. It means this. On the next line, it's just a reminder that the infinite sums are an abstraction that sometimes makes us lose our way. We have to remind ourselves, we're just looking at a sum that goes this way. And now part B says, deduce a formula for the coefficients. By the coefficients, we mean these parts. We can get a formula for the coefficients. We'll have a formula for a Taylor series representation or a formula for a power series representation that doesn't immediately require something like, say, a weird adjustment of the geometric series, which was what the last section was all about. So this is going to give us way more general methods. We can represent much more functions this way. And here's how it goes. We take f at one particular value here. There's one value that simplifies this tremendously. It's the center. We plug a inside of f. Then from where the red dot is to the right, everything is canceled. We have a minus a times c1, a minus a squared times c2, and so on. All we get out of that is c naught. So that's the first thing that happens. We're trying to find a formula for the coefficients. There's infinitely many coefficients, but we've got one down. This is all about pattern recognition now at this stage. We can find the pattern, we'll find the Taylor or Maclaurin series. But this line is no good to us any longer. We used it up. We need another line just like this. So what we're doing next is, let's scroll for just a moment. We're going to use this part. This came from section 11.9. That's kind of the purpose of 11.9, not to dump a whole bunch of theorems on our head at once. This was the old theorem from the last time. We want this part about differentiability. So let's bring this up just as a temporary reminder as a screenshot. It tells us, even though that there are infinitely many terms on this line at the red dot, equally abstract on the bottom line when it's expanded, still infinitely many terms, the theorem screenshotted below still applies. That's the wrong part. Let's get a different screenshot. This part still applies. We can differentiate the whole thing. And that's exactly what we want to do. Differentiate this exact entire line by doing term by term by term differentiation. That's the whole content of that big theorem. So now we'll have, let's write this as maybe slightly indented, f prime of x equals derivative of a constant goes to 0, so that part's just gone. And we're left with c1, constant multiple rule, that derivative is 1. Here, we're now using chain rule, not exactly, derivative of the inner function is a 1. But power 2 is going to multiply c2. So 2c2, x minus a. Rinse and repeat. We're differentiating infinitely many terms, so next one is 3c3, x minus a squared, 4c4, x minus a cubed, 5c5, x minus a power 4. And just as a reminder, good idea to go plus dot dot dot. There really is infinitely many more terms out there. We just didn't list them, so we're not going to differentiate them either. So that's our derivative. And there is a pattern emerging here. We can now evaluate f prime at the center again. Doing f prime at the center on this line only gave us one piece of information, but this is like a whole new equation to regard, a whole new power series on the derivative f prime. We can feed a inside this again and get something new. F prime of a is exactly just c1. So the c1 survives. Everything else is just completely annihilated. Doesn't look like really a pattern on the coefficients. Well, maybe there kind of is. First coefficient is the function at the center. Second coefficient, c1, is the derivative of the function at the center. That continues forever, then we've got the pattern. But we need more data points to really see this pattern, so we need just a higher order derivative. We'll go to f double prime of x and see what happens next. Second derivative of x, same idea, different computation. c1 goes to 0 as a constant. X minus a goes to 1, so this is just 2c2. Plus, here power 2 comes down, so it's 2 by 3. c3, x minus a to power 1. But notice the odd way we're writing this down. Because we are pattern hunting, it's a bad idea to actually multiply these together. I will mention this comment as we go throughout the notes. Even in a generic problem, we are really still looking for patterns, just like in example 1. And 2 times 3 reminds me of a 3 factorial. 6 might hide the fact that there's a factorial in there. Didn't look like there's factorials by the first two terms, but 2 is 2 factorial, 2 by 3 is 3 factorial. We start to wonder if that pattern is real. Differentiate this term. 3 times 4 times C4, x minus a power 2. That's not a factorial yet, but on the third order derivative, 2 comes down, and it's 2 times 3 times 4. That would be a 4 factorial. So this is a 2 factorial, 3 factorial, and then almost 4 factorial is coming up on this one. Then plus derivative from over here is 4 by 5, C5, x minus a power 3. So we're almost there. Next step is not to do f prime of a any longer. The f prime equation is now no longer good to us. We do double f prime at a. So double f prime at a. This time gives us not C2, we get 2 by C2. This is telling us already that the pattern we might have suspected on the first two terms does not hold. The function, or excuse me, the coefficient Cn is not the function at the center, the derivative at the center, and so on. It looks like it might involve a factorial, in fact. But one thing that's tricky about trying to work with these patterns is you might need the third order derivative, or in some rare cases, even the fourth order derivative we'll see is effective. Let's go one higher. Let's see what we can find at the third order derivative, and then debate if we need a fourth order one. Any questions at all, folks, to this line on what we've developed so far? Okay, let's take the pattern further. I forgot over here on the second order derivative. Good call, just as a reminder, there's still infinitely many terms. They are being differentiated, but we just never copied them down. And now the third order derivative, you can either write as f 3 different prime symbols, or if you like this convention, that does indicate the third order derivative. You do need the parenthesis though, because f3 and f3 that way have totally different meanings. This is repeated function composition. This is third order derivative. So let's go f3 at x, or f triple prime if you prefer. It means we're differentiating this term. That term goes to 0, so we differentiate over here. That leaves behind 2 times 3 times C3. X minus a is gone. Let me control Z that. Plus 2 comes down on this one. So 2 times 3 times 4. X minus a to power 1. 3 comes down on this one. Plus 3 times 4 times 5. X minus a power 2. And then infinitely many more terms. So if I wrote that in as a 6, and then this one as a 24, and then this one as a, let's see, that looks like a 60, I probably would never see the factorial pattern whatsoever. But expanded like this, not multiplying them together, it becomes pretty striking. We can say third order derivative of f, now at a, is going to give us that back with the 2 times 3. So it's now 2 times 3 times C3. At this stage, let's start actually deducing that pattern. So the goal was deduce a formula for the coefficients. That means we should solve for C naught in every single one of these lines. Let's write on the first line. Solve for C, rather. The first line is C naught. C naught equals f at a. And that does look weird, but we're allowed to divide by 0 factorial. I want a 0 factorial in there to match up the 0 on the coefficient index. 0 factorial is 1, so we didn't change this equation. We're just trying to fit a pattern next. Down below on this one, we'll say that this implies C1 f prime of a divided by 1 factorial, which is in fact 1. So we have a pattern going. Now C2 f double prime at a divide by 2, sure, but 2 is also equal to 2 factorial. Keeps the pattern going, so it looks like it's a striking pattern. The index determines what order derivative you're taking, whether if there's nothing here, that's the 0th order derivative, you could say if you'd like. C1 leads to the first order derivative, C2 leads to the second order derivative, and we appear to have factorial in the denominator. So we'll say here, if the pattern is to continue, C3 will be the third order derivative, divide by 2 times 3, which is in fact a 3 factorial. And we can do one even better. On this line, you notice you might not have needed to differentiate these to come up with the next one. If f prime is C1, f double prime is 2C2, f triple prime is 2 times 3 times C3, then the fourth order derivative of f at A, just matching the pattern right above, should be equal to 2 times 3 times 4, C4, which would then imply that C4 equals fourth order derivative at the center A, forgot that on the line right above, divide by 4 factorial. And again, the pattern is really, really striking. We can say as a overall conclusion to part B, where it says deduce the formula, let's say, therefore, here's our deduction. The coefficient Cn at any index n, so this is for n bigger than or equal to 0 as an integer, Cn is going to be f at n at the center A, divide by n factorial. This is how the formula starts to get written in, but it has the understanding that if we do at 0, let's write this in as just an overall statement, f0 at A is just ordinary f at A. It's the, like we mentioned, the 0th order derivative, which just means an original function itself. So we've got a pattern down, and that's really pretty weird when you think about this. If you write down f of x is any power series, here it is, then just start expanding and differentiating as you go, you are automatically just cornered into this conclusion. The coefficients of the power series have to take on this new format. That's a big statement, but that's what allows us to get going in section 11.10. We're going to try out essentially this exact process, maybe in a slightly different tabular format. I want one column with the functions on the left, another column with the functions derivative on the right. But aside from that, these exact steps give us the representations we're looking for. So let's take a look into the next part of the notes. Les, any questions at all at this page here, folks? Okay, next part of the notes is just a reminder of some tools that we have from the prior sections. So this is the definition of a power series in 11.8. These were the methods to differentiate and integrate from 11.9. And this is the good old ratio test from section 11.6. It is a huge tool in this section because this time, when we go to actually represent something as a power series, we actually have to use the ratio test. Since we're not going to be directly calling geometric series any longer in this section, unless we just find out it works, which would be a rare problem. So here's the new material we did through example 1. Just paraphrased, the coefficients are the nth order derivative at the center divided by n factorial. And when it says a power series representation at A, this is just another way to say the center is A itself. So using that as a formula, f of x can be represented this way. So if f has a power series representation at A, so that's the center would go there. If the radius of convergence is R, then that would mean this function f of x has a definite ordinary meaning as a literal function for all x values within a distance R of its center. It has a meaningful definition as a real function. So we call this the Taylor series centered at A. And theorem 7 is the same exact thing. It's just the specialized Maclaurin series, which means we're centered at 0. So that's the Maclaurin series. It looks a little bit simplified, but that's because we just have x to a power rather, well, I was pointing at the wrong thing. We just have x to a power here rather than x minus a to a power. So the concepts are really the same. It's all about the center. Example 1 is going to be about the Maclaurin series, and then example 2, we'll try this all out for Taylor series next. And looking at the time as well, let's see, we go to, what was it, 7:30 to 8:37. We'll make sure we don't break a problem in half. These are kind of longer problems. We might just do example 1, end a little bit earlier, so we're fresh when we give a look at example 2, which is trickier. So here's what the steps would look like. Let's highlight this as the formula and walk it down as we work. As far as the final exam goes, I really only have the opportunity to ask just like one of these questions. We are getting to the end of the course material. I can't just load it up with a bunch of questions from here. So expect a question from part 1, this one right here, and maybe another question from part 2, which would be a slightly more applied question. But here's how we're going to start this off. Step 1 is to do the following. Let's indicate center is a equals 0. Again, only because it said Maclaurin series. That means we're going into a 2-column system where we put in f of x, e to the x, and f at the center 0 as well. We need to do both evaluations. That's going to be e power 0, but that means it's just a 1. So the center equals 0 always gets dropped in here. And this whole thing, this whole table we're developing is just all that step 1. Now next, we begin differentiating. Our goal here is we're really pattern hunting. And if we go f prime of x, this is a nice one to start off. The pattern is not too extreme, right? Because the derivative is never going to change on us. So on row 2, derivative of f at x is e to the x. So the valuation at the center, still a 1. This is a case where you might not have too many rows here. Let's maybe go to the second order derivative. But there's already a pattern. Second derivative is e to the x. Second derivative at the center, still 1. And maybe one more just for good measure. Third derivative at x. Nothing has changed, still e to the x. Third derivative at the center is still just e power 0, so 1. So with all this information, we can now go to the next step, which would be to make that a little bit bigger so we can actually read that. We want to find the value of that part as a formula. Once we get it, this whole part we call Cn, and then we could just feed it back into theorem 7, the Maclaurin series representation, which shouldn't feel too different from the entirety of the last section where we were just relating everything into that format. So this takes us now to step 2. And you could break up step 2 in a couple different ways. Let's write out maybe f n at the center 0 is going to be equal to, looking at the pattern emerging, there really isn't much of a pattern. It's just always a 1, no matter what order derivative we take. So we say it's a 1 right here. Sometimes step 2 is pretty involved, so the next problem that we're going to look into is one of those cases. But as a warm-up problem, this is just right. We just get a 1 out of there. Now we have the numerator. If we'd like, we could break this down into step 3, just to write out what is the coefficient, Cn, that's indicated. Cn is the nth order derivative at 0 divided by n factorial. So that would then tell us that the formula for Cn is just 1 over n factorial. That gets us in a really good position next. Step 3 is to put it together. We're trying to now write out f of x in this way, using the representation. Rather, that's step 4. There's quite a few steps, some of them pretty short. Step 4, let's write out that e to the x That's the f of x part right here, but it's kind of nice to indicate the specific function, e to the x, as being the one we're finding the representation for. This is a sum from 0 to infinity. And following the formula down below, all we need to do is grab this 1 over n factorial, multiply it by x power n. So that's our whole statement there. That can be simplified a little bit better. It's a summation from 0 to infinity of x to the nth power division by n factorial. So somehow, some way, this represents e to the x. But we want even more. We want to also find radius of convergence. This is where we start working a little bit more, step 5. We never had to do this in the prior section, 11.9. In fact, it's a really bad idea because we never had to use anything aside from the geometric series test, which gave us all information. But for the power series like what we're using, all we've got is a ratio test. And the ratio test has this problem that we have to maneuver through whenever it happens. What we hope is the limit is L and it's less than 1 for all x. That means we don't even have to do too much work on the ratio test, really. So let's give this step 5 next a try. Step 5 is just using ratio test. Because it's not good enough to say you have a way to represent e to the x. Sometimes these representations only work on really small domains next to the center, or sometimes the domain is all real numbers, but we have to find that out. So in the ratio test, let's put this on the next page maybe so we can fit this all. We always did the ratio test in a particular way, so let's copy that as well. We have an plus 1 equaling x to the power of n plus 1 divided by n plus 1 factorial. Then we had an. Oftentimes we call this summation equal summation an. Here I'll write in that an equals x power of n over an n factorial. Then the ratio test, it's the limit. N goes to infinity of this part in that format. You can factor here if you like to just streamline the canceling. Now n plus 1 times n factorial. Then we multiply it by reciprocal over here. That's now n factorial over x power of n. We always expect a cancellation with ratio tests. That's part of what makes it work so well. And here's these cancellations. Factorials are gone and x to a power are gone, leaving behind absolute value of x outside the limit. It's a limit as n goes to infinity of 1 over n plus 1. So that's where the ratio test settles. The limit's fast. The limit of that is just automatically a 0. So this is absolute value of x times 0, which is 0. Take another look at that ratio test. We are in case I. We have a limit which is 0. And that 0 limit that we provided did not depend on x. Whatever x you chose, it's wiped out, multiplied by 0. So this is less than 1 for all x. So we could say, therefore, the radius of convergence is infinite. So this is the representation, and that's its radius. If you left your work in this format on paper, that's totally fine, but it's honestly kind of hard to read. Better to state the whole answer as, therefore, e to the x is a sum from 0 to infinity of x power of n over n factorial. And that's such a great representation. This convergence is strong, absolute convergence, because we use the ratio test. And the domain is all real numbers. It's infinite. So that's a huge statement. Let's just try this out to see, what have we done? That's the next challenge with doing this kind of problem, is trying to understand what all this means. So say, for example, you did maybe e power 0.5. Desmos did something here and got the value 1.64872 and so on. But you know what? What Desmos did is not too different than what we might do. We could compute this as well. 0.5 is a value on x. When we plug in 0, it's going to be a 1. That's the index n is 0. When the index n is 1, we have 0.5 to the power 1 divided by 1 factorial, which is 1. Look how fast these are actually summing together. When we index up the index to 2, we go 0.5 squared divide by 2 factorial, which is just 2, and already 3 terms, the first of which is just a 1. Fast convergence. We're accurate to 1 decimal place. Let's make this our last one. Plus 0.5 cubed over 3 factorial, 1.64. We're accurate on the hundredths already. The convergence is remarkably fast because of the factorial. Factorial grows rapidly, and so this is a really, really effective way to represent e to the x. But it's not just about e to the x. Remember, it's also about, if you could get a representation for e to the x, you can get a representation for e to the x squared, which means you can now integrate that thing. The integral is just another power series like this, same radius of convergence. So that's where all this kind of stuff is going, but congratulations, we did our first Maclaurin series. The rest of them are similar to this one. Any questions at all getting down to that result? Okay, well, when we come back on Wednesday's class, we'll mainly just be in this section. We might take a look at the next one, but I feel like we'll finish 11.10 more likely when we come back on Thursday. So we're not rushing through these harder problems. But have a great night, folks. I'll see you all on next class, Wednesday. Thanks. We are, yeah. I have one that's so you have to re-index it.
Yeah, okay, I figured, you're just oscillating between 0, 1, and -1.
Exactly.
Taking the derivative.
So we take all the 0 values out, we just delete them, and we re-index on the non-zero values, which is going to be all the odds.
Just
Yeah.
1, -1, 1, and then just keep going like that.
Sorry, say again.
So just 1, then -1, then 1, like taking the derivative of each one.
Yeah, in a sense, it'll be -1 times whatever the prior function would have been.
Oh,
So yeah, if we had like, this one is hyperbolic sine, same idea. We'll have hyperbolic sine at 0 is 0, derivatives hyperbolic cosine. And then, yeah, you get the 0, 1, 0, 1 pattern repeating here.
so what do you end up putting for f to the nth derivative of 0? It ends up becoming like -1 to the power of n. It just goes to -1 power n. So it has to be.
Yeah, exactly.
That's
It's gonna be a weird one.
the actual. There's no way to get rid of them. The actual
Yeah.
is like -1 to the power of n, x 2n plus 1 over 2n plus 1 factorial.
Yeah, exactly. And the 2n plus 1 is just the way you represent an odd integer.
Yeah.
And the sine function is an odd function, so it all just seems to make sense in a weirdest way. We'll see it happen.
1 minus x squared over 2 factorial.
Yeah.
I was trying to do the sine one. I don't know.